Welcome to the Basic Foundation Physics lecture series. This is our lecture number 1, and in this lecture we are going to cover some basic concepts of vectors and kinematics. So this lecture will include the definition of physical quantities, definition of scalar and vector quantities and difference between them, representation of a vector, different types of vectors, and we will also discuss some fundamental concepts of kinematics in this lecture. So before we arrive at the definition of vector quantities, let us first understand what do you mean by physical quantities. So quantities having magnitude or numerical value are called physical quantities. In physics, we are going to deal with physical quantities only, that is quantities to which we can assign a numerical value. Physical quantities are further divided into two categories: scalar quantities and vector quantities. Scalar quantities are the quantities in which only magnitude is needed, but their direction is not needed for their description. All scalar quantities follow simple laws of algebra. Few examples of scalar quantities are mass, distance, speed, time, current, etc. On the other hand, if a physical quantity, in addition to its magnitude, also has a specified direction, and along with these two conditions, if it obeys parallelogram law of vector addition, then that physical quantity is a vector quantity. All vector quantities follow vector laws of algebra, which are completely different from our simple laws of algebra. We are going to learn vector algebra step by step in our next lectures. Few examples of vector quantities are displacement, velocity, acceleration, force, etc. Let us now discuss a very important question, which is why is it important for us to know whether a physical quantity is a scalar quantity or a vector quantity? The reason is their algebras are completely different. We should always keep this in our mind that we cannot apply simple laws of algebra when we deal with vector quantities. So after our brief discussion of vectors, let us now learn how to represent a vector. So if a physical quantity is denoted by a symbol A, then an arrow or a dot over the top of A or even a bold letter A will indicate that this physical quantity is a vector quantity. These are the symbolic representations of a vector, and geometrically it is represented by a line with an arrow indicating the direction of the vector. This point here is known as tail of the vector, and this point is called head of the vector. Length of this line will give us the magnitude of this vector, while the direction in which this arrow is pointing will give us direction of this vector. Okay, so our next topic is magnitude of a vector. So let us first understand what is the meaning of magnitude of any physical quantity. Magnitude of a physical quantity is nothing but its numerical value along with its units. If a vector is represented by a symbol A, then its magnitude will be represented by mod A or simply A. Let's take an example. We have a force of 2 Newton and it is acting in the east direction. So this is how we write this. Vector F is equal to 2 Newton, and we know that this force is acting in the east direction. And if we have to draw this geometrically, then we will take a reference, and the length of this vector will be equal to 2 and the direction will be towards east. If magnitude of this force is also asked, then magnitude is denoted by mod F or simply F, and magnitude will be nothing but its numerical value with its unit. So magnitude of this force is equal to 2 Newton. This is the last topic of our vector section, and in this topic we are going to learn about different types of vectors. First one is zero vector or a null vector. Zero vector or null vector is represented by vector 0, And as the name implies, if any vector has a magnitude equal to 0, then that vector will be called 0 vector or null vector. But what about the direction? So we can take any arbitrary direction to define this vector. What does this mean? So we have a block and we are exerting a 0 Newton force on this block. So in reality we are not exerting any force on this block, but we can say that we are exerting 0 Newton force in the east direction, or we are exerting 0 Newton force in the north direction, because it won't make any difference as we are not applying any force on this block. So we can take any arbitrary direction to define this vector. Next one is parallel vectors and anti-parallel vectors. If two vectors points in the same direction, then they are called parallel vectors. On the other hand, if two vectors points in the direction opposite to each other, then they are called anti-parallel vectors. Next one is coplanar vectors. So as the name implies, vectors lying in the same plane are called coplanar vectors. We can also say that if heads and tails of different vectors lie in the same plane, then they are called coplanar vectors. Okay, so next type is equal vectors. This is very important for us. Two vectors are said to be equal vectors if they have same magnitude as well as same direction. So if vector A is equal to vector B, then their magnitudes should be same and they should also point along the same direction. We will take another example. If we have two forces, let's say vector F1 is equal to 2 Newton and it is acting along east direction, and another force vector F2 is also 2 Newton and it is acting along north direction. Although magnitude of both forces are equal, but they do not point along the same direction, so these two vectors are not equal. Next type of vector is unit vector. So as the name implies, if magnitude of any vector is equal to unity or 1, then this vector will be called unit vector. A unit vector in the direction of vector A is represented by A cap, and we know that mod of A cap, which is nothing but magnitude of A cap, will be equal to unity. Next one is negative of a vector. So negative of a vector A will be represented by minus of vector A, and it is defined as the vector having same magnitude but opposite direction. So if vector A is represented like this, then minus A will have the same length but its direction will be opposite to this vector. Let us now discuss few important points regarding vectors. So a vector can be displaced parallel to itself and its value will not change. While displacing a vector, we should keep this in our mind that we cannot change its magnitude, which is equal to length of this line, and we cannot change its direction. Next important point is that we cannot rotate any vector by an angle other than multiple of 360 degrees. Because if we rotate any vector by an angle theta, which is not a multiple of 2 pi, where n is integer, So the direction of this vector will be different than the direction of original vector, and this vector will be a completely different vector. So we can displace a vector parallel to itself, keeping its magnitude and direction constant or fixed, but we cannot rotate a vector by any angle which is not a multiple of 360 degrees. And the third important point about vectors is the angle between two vectors is defined as smaller of the two angles when their tails are joined together. So if tails of two vectors are joined together, then two angles are possible. If one is theta, then the other angle is 360 degrees minus theta. So smaller of the two angles, which is theta, is the angle between these two vectors. We will now move on to our next section, which is kinematics. Kinematics is a branch of physics which deals with study of motion. But before we begin this section, the very first thing that we have to understand is the concept of rest and motion. Let me ask you a question. If you are traveling in a car, are you at rest or in motion? Let me ask you another question. When you are traveling in a car, you see trees going past you. Are those trees at rest or are they in motion? To answer these questions, we have to first understand how do we define rest and motion. So there is no meaning of rest or motion without the observer. Nothing is in absolute rest or in absolute motion. An object is said to be in motion with respect to the observer if its position changes with respect to that observer. It may happen both ways, either observer moves or object moves. Or in simple words, we can say that motion is a combined property of the object and observer. Okay, so this is how we define rest and motion in physics. If position of object does not change with time with respect to an observer, then the object is said to be at rest with respect to the observer. On the other hand, if position of object changes with time with respect to an observer, then the object is said to be in motion with respect to the observer. We will take an example to understand this more clearly. So we have a ground surface and a cart is moving with some speed on this ground surface. There are two persons A and B, and we are assuming that distance between them remains constant. Both A and B are standing on this cart. So with respect to this cart, they are not moving. There's a tree on ground surface. This tree is obviously at rest with respect to this ground surface. If we take A to be an observer, so with respect to A, position of B is not changing with time, although this cart is moving, but with respect to A, position of B is not changing with time, so B is at rest with respect to observer A. This tree is stationary, but with respect to observer A, its position is changing with time because this cart is moving. So tree is in motion with respect to observer A. But if we take tree to be an observer, then with respect to this tree, position of A is changing with respect to time because this cart is moving, so separation between them is increasing. So A is in motion with respect to tree. Similarly, B is also in motion with respect to observer, which is the tree. So we have to define a frame of reference to solve problems in kinematics. And how do we do that? So easiest way to set up a frame of reference is to take three mutually perpendicular axes, and we are naming these x, y and z. These are origin O, and coordinates of any point would be x, y and z. So if any one or more coordinates will change with respect to time, then we will say that with respect to this frame of reference, this point P is in motion. How do we define motion in one dimension? So this is very simple. If any one coordinate, either x or y or z, is changing with respect to time, then we will say that this motion is in one dimension or a linear motion. And if any two coordinates changes with time, then we will call that motion in two dimension. Similarly, if all three coordinates changes with time, then we will say that the motion is in three dimension. So it all depends on our frame of reference. Next up we have distance and displacement. Distance is defined as the length of the total path traveled, while displacement is the shortest distance between initial and final point. We will take an example to understand these concepts. So let's say a person is traveling from point A to B via this path. So total distance of this path will be the distance covered by the person, but the shortest distance will be the magnitude of displacement. Distance is a scalar quantity, while displacement is a vector quantity. We have already discussed that for a vector we need to know its magnitude as well as its direction. Magnitude of displacement is defined as the length of the line joining its initial and its final point. So in this case, this over here is our initial point and this is the final point. So magnitude of displacement is defined as the length of line joining initial and final point. And what about the direction? So direction of displacement is from initial point to final point along the line joining initial and final point. We will take few more examples. In this example, it is given that a ball is thrown vertically upwards with speed v and it will reach a maximum height h, and we know that it will return to the same point A following the same path, and we have to find a magnitude of distance as well as magnitude of displacement in this case. So distance is nothing but the length of the total path traveled. So we can write the length of line AB plus length of line BA. So it is nothing but h plus h. So 2h is the magnitude of distance. And for calculating the magnitude of displacement, we have to join initial and final point. So we know that the initial and final point in this case are the same. So length of the line joining initial and final point will be 0. So magnitude of displacement is also 0. We will take one more example. In this example, it is given that a particle is moving along a circle of radius r, and we have to find the distance and magnitude of displacement when it travels from A to B, A to C, A to D, and when it completes one complete revolution. Yes, so let us try to solve this. So when particle is moving from A to B, we know that radius of this circle is r, and the total length of the circumference is 2 pi r, and this distance is 1/4 of the total circumference. So distance will be 1/4 of the total length of circumference, and it will be pi r by 2. And what about the displacement? So we know that For finding the displacement, we have to join initial and final point, and length of that line will be our magnitude of the displacement, and the direction will be from point A to point B. So we know that radius of this circle is r, so this distance is also equal to r, and this is 90-degree angle. So from Pythagoras theorem we can say that this distance is nothing but root 2r. So magnitude of displacement is root 2r, and direction of displacement will be from point A to point B. In the second part of the question, we have to find distance and magnitude of displacement when the particle is moving from point A to C. We know that the distance of this part will be 1 by 2 times distance of the circumference, because it is a semicircle. So distance traveled by the particle will be equal to pi r, and magnitude of displacement will be the length of the line joining point A to C. So this length is r, this is also r, so total length of this line is 2r, and direction of displacement is from point A to C. In the next part, we have to find distance and magnitude of displacement when it travels from point A to point D. So length of this part will be 3 by 4 times the length of total circumference. So it will be 3 pi r by 2. And for displacement, we have to join initial and final point. So length of this line AD will give us magnitude of displacement, and we have already calculated the length of this line. So length of this line AD will be equal to root 2r, and direction of displacement will be from point A to point D. In the next part, we have to find the distance covered by the particle when it completes one revolution, and we know that this distance is equal to total circumference of the circle, and magnitude of displacement in this case will be equal to 0 because initial and final points are the same. The last topic of our lecture is speed and velocity. And in this topic, we are going to discuss the definition of speed, average speed, instantaneous speed, definition of velocity, average velocity, and instantaneous velocity. So the rate at which distance traveled by particle is changing is called speed. It is a scalar quantity, while the rate at which displacement of particle is changing is called velocity of the particle, and velocity is a vector quantity. Next up is average speed and average velocity. So average speed is defined as the ratio of total distance traveled and total time taken, while the average velocity is defined as the ratio of total displacement and total time taken. We will now discuss the definition of instantaneous speed and instantaneous velocity, and later on we will try to understand the difference between average speed and instantaneous speed, and average velocity and instantaneous velocity. So instantaneous speed is nothing but the speed of any object at any particular instant. Similarly, instantaneous velocity is also defined as the velocity of an object at any particular instant. These terms are frequently used in kinematics, so students are advised to give special attention to these definitions. Let us discuss few important points which are related to distance, displacement, speed, and velocity. So distance traveled by a particle is always greater than or equal to the magnitude of the displacement. So if a particle is traveling from point A to point B via this route, so length of this path will give us the distance, but the length of the line joining AB will give us the magnitude of displacement. So obviously this length here in this case is greater than the length of line AB. But if this particle travels in a straight line without changing its direction, then in that case the distance traveled by this particle will be equal to magnitude of the displacement. So distance is equal to magnitude of displacement only when the particle is moving in a straight line without changing its direction. Since distance is a scalar quantity, so it will always be positive, but the displacement is vector quantity, so it can be positive, negative, or zero. Let's say we are throwing a ball from the top of a tower of height h in vertically upward direction, and this initial point is A. So it will reach to a maximum height, and at the maximum height its velocity will be 0, and we are naming this point as B, and it will return to the ground. The point where it hits the ground is D, and the point where it crosses its initial point is C, and we are taking vertically upward direction to be positive. We are also assuming this height to be equal to h naught. So for A to B, distance traveled by the ball is equal to h naught, and displacement of the ball is plus h naught because it is in the upward direction. For A to C, distance traveled by this ball will be equal to length of AB plus length of BC, which is equal to h naught plus h naught, which is equal to 2h naught. And the displacement of the particle while traveling from A to C will be equal to 0 because the length of line joining point A and point C will be equal to 0. And for the path A to D, distance traveled by this ball will be equal to length of AB plus length of BD. So length of AB is h naught, and length of BC is also equal to h naught, and length of CD is h. So total distance of this particle will be at 2h naught plus h, but the displacement of the particle will be minus h because the length of line joining A to D is equal to h, and displacement in this case is in the negative direction. So displacement in this case when ball is traveling from point A to B is positive, and when it returns to the same point, that is C, it is equal to 0, and in the last case when it hits the ground it is negative. We can also conclude our third point based on this example, which is distance never decreases, but displacement may decrease in few cases. Next important point that we have to remember is that average speed is always greater than or equal to magnitude of average velocity. We know that average speed is nothing but total distance traveled upon time, and average velocity is total displacement covered by time. So if we divide distance by time and magnitude of displacement by time, so this equation will become distance by time is equal to average speed, and displacement by time is equal to average velocity. So average speed will always be greater than or equal to magnitude of average velocity, and we had already discussed that distance is equal to magnitude of displacement only when particle moves in a straight line without changing its direction. So average speed will be equal to magnitude of average velocity when the particle travels in a straight line and without changing its direction. So the last but the most important point is that instantaneous speed is always equal to magnitude of instantaneous velocity. And to understand instantaneous speed and instantaneous velocity, we have to first understand how do we define an instant. So an instant is a time interval which which is very close to 0, which is not equal to 0, but it is close to 0, or we say that the time interval is tending to 0. So since this time interval is very small, so we say that in that time interval the distance traveled by particle and magnitude of displacement covered by the particle remains same. So the speed in that time interval, which is equal to instantaneous speed, always remains equal to magnitude of instantaneous velocity. We will now take an example to understand the terms average and instantaneous that we just used. So we are throwing a ball vertically upwards with initial speed v0, and you may have observed that its speed at all the points will not remain constant, but it will decrease as it rises upwards, and at the highest point its speed will become 0. So instantaneous speeds at all different times will be different, but if we have to calculate the average speed, it will be nothing but the total distance traveled upon total time taken. And let's say total time taken by this ball to return to its original point is t naught, then average speed will be distance traveled 2h upon t naught. Similarly, if we have to calculate the average velocity, so average velocity is defined as the total displacement upon total time taken, and in this case we have already discussed that displacement of particle is 0 and time taken is t naught, so average velocity is 0. We will now solve some questions based on the concepts we just discussed. So in this question, a person is covering half distance with the speed v1 and the next half distance with the speed v2, and we have to find the average speed of that person. So if we assume the total distance to be x, then this distance will be x by 2, and next half distance will also be equal to x by 2. It has been given that for the first half person is traveling with speed v1, and for the next half person is traveling with speed v2. We know that distance is equal to speed into time, so time will be equal to distance upon speed. Let's calculate the time taken by a person to travel from point A to C. So distance between point A and C is x by 2 and speed is v1. So time will be x by 2 v1. Similarly, time taken by a person to travel from point C to D will be distance, which is also equal to x by 2, and speed, which is equal to v2. So time taken will be x by 2 v2. Now we have to find the average speed of the person during the whole journey, and we know that average speed is nothing but total distance traveled upon total time taken. So total distance traveled is x and total time taken will be summation of time taken to travel from point A to C and time taken to travel from point C to B. Let's substitute these values. So on simplification, we will get our final answer, which is 2v1 v2 upon v1 plus v2. Let's solve a similar question based on the same concept. So in this question, a person is traveling with the speed v1 for some time, let's say t, and for the next equal interval of time it is traveling with the speed v2. We are assuming distance between A to C to be x1 and distance between C to B is equal to x2. We know that distance is equal to speed into time, so x1 will be equal to v1 into time t, and x2 will be equal to speed, that is v2, into time taken, that is t. So average speed will be total distance traveled upon total time taken. Total distance traveled is x1 plus x2 and total time taken is t plus t. x1 is equal to v1 into t and x2 is equal to v2 into t and total time is 2t. So t and t will be cancelled. So average speed in this case will be v1 plus v2 by 2.